We're happy to have Gil Cohen here from Caltech. Gil is going to give an experiment we're doing this year. We already had a couple, so Monday talk followed by more detailed Tuesday talk. So he talked to us about constructing Ramsey graph.
So hi, thank you everyone. So I'll talk about constructing Ramsey graphs, and the longer title is the one below, but you can forget about it. And feel free to ask any question during the talk. We're not hurrying now, because tomorrow we also have a more detailed talk anyhow. So, okay. So if you want to kind of put in one sentence what is Ramsey theory, then maybe this would be a good candidate. This is the study, this is the field that studies the unavoided presence of small or local structure in globally unstructured objects. There are many examples for this kind of examples of Ramsey theory results, the simplest of which is probably the pigeonhole principle, but maybe the most famous is the one that introduced by Ramsey, kind of implicitly in his paper. So in this talk, a graph will be an undirected graph. And we say that a graph is k Ramsey, k is some integer, if it has no k clique and no k independent set in it. It kind of avoids this. So in this case, the fact that this is a general graph is the global structure, global unstructured object. And the structure that we are interested in not having is being like monochromatic, being either a clique or independent set. And kind of famous theorem by Ramsey from 28 says that there is no half log n Ramsey graph on n vertices. Namely, any n vertex graph that you will take would contain either a clique of size half log n or an independent set of size half log n. So you can never avoid this structure when you look at kind of windows of this size on the graph. Yeah, right.
The bound, he has no bounds in his paper.
I see. Just it's a paper in logic, right? It's just a paper.
Yeah. Doesn't matter. I mean, it proves this statement.
Right. I see. Okay. Yeah, I couldn't find it in the paper, but I kind of assumed it.
So the paper is the defect actually. It's a bound that gives these.
I see. Okay. So so maybe just. So for example, here is this some graph, and you can always find in this graph a subgraph or some subset of the graph such that the induced graph is either clique or independent set. In this case, it's an independent set. I think it's much larger than half log n in this case, but no. Okay, so complementing that result, there is the result of Erdős that proved that there exists a 2 log n Ramsey graphs. So there are graphs on n vertices such that if you look at windows 4 times as much as these windows, then you will never encounter a clique or independent set. You can avoid this structure if you look at slightly larger windows. And of course, one interesting question is what's the right number here, not just the asymptotics. But actually, we won't go into that direction. There is some research on that direction, but we will consider actually this result we'll consider we'll focus on this result. So if you look at this proof, so this is a very famous paper by Erdős. I not think that it's because of that result mainly, but because it's kind of the paper that inaugurated this probabilistic method that is very useful. It may be not the first application, but it's certainly the paper that's most influenced in that respect. Shannon also used this kind of method before. But anyhow, what Erdős did here is he gave a probabilistic argument, which proved that if you take essentially a random graph on n vertices according to uniform distribution, then with high probability that graph will be 2 log n Ramsey. So actually most graphs have this property. But this is a non-constructive proof. Namely, it doesn't give you an example of a graph that has, so given n, you don't get an algorithm that in poly n time produces the graph that has this property. It does give you a randomized algorithm that does so. But Erdős raised the problem of matching his proof with a constructive proof. So I'm not sure that by a constructive proof Erdős actually meant give me a poly n time algorithm, etc. But this is kind of the point of view that we have today from complexity point of view. So this is the problem that we are interested in. So we want to devise an algorithm that, given n as input, runs in poly n time, or actually some stronger notion of explicitness would be achieved here. And that graph would be C log n Ramsey for some constant C. Not necessarily 2, but 100 log n Ramsey would be great. So this is the problem that we consider. And actually, according to some versions, Erdős offered $100 for solving this problem, which is not a lot of money, but if you kind of, it's a lot of Erdős money, I think.
Probably offers much more for determining the right constant between
Right.
1.5 and 2.
Right. Yeah, I think this is the highest also, right? If I remember correctly. Ah, wow. Yeah, so we'll talk about.
Who pays these prices?
I think now Graham in China. Yeah. Okay. So this is the problem at hand. Let me just go briefly over previous work. So here's the who did it, and here k of n means what's the k that is supported. So in the construction, if you look at subgraphs of induced graph on k vertices, you won't find an independent set of. And you want k to be as small as possible. So Erdős proved that non-constructively you can get k which is 2 log n also. It's actually 2 plus little of 1, but kind of ignoring this. And there was a sequence of paper that eventually achieved something which is kind of between the trivial n and the ideal 2 log n, which is 2 to the square root of log n also. And there was also explanations for why this is kind of a bottleneck for some of the techniques that were used. And so this is the line of, I hope I'm not missing too much references, but this is the line of work that considered this problem of constructing Ramsey graphs. But there is actually a stronger notion of Ramsey graphs which are bipartite Ramsey graphs. And in this setting, you want to construct a bipartite graph on n vertices of each side, say, that avoids a clique or independent set in the bipartite setting. Namely, if you take any k vertices here and k vertices there won't be an independent set or a clique. And this is a strictly, this is a non-easier problem in the sense that if you have that bipartite construction, you also have the standard construction. And for a while, it seems that this is a much harder problem. I mean, the folklore result says that any Hadamard matrix you will take gives you something that is twice as better than the trivial n bound. But this is a folklore. I'm not sure who actually proved that. You can do it by Lindsay lemma, Fourier analysis, stuff like that. And this was slightly improved. So notice the year, right? So much later after Franken and Wilson, for example, this was slightly improved by Pudlak and Rodel. And then in a kind of breakthrough paper by Barak, Kindler, Shaltiel, Sudakov, and Vigdeson, they actually achieved something that is little of n. So it's not as good as what you know for non-bipartite graphs, but it's great. I think it's like n over log n if you look at it. I can vouch for n over poly log n, but I think it's n over log n or so. And this paper actually, besides the result itself, it introduces a technique which they call the challenge response mechanism, which we build on. I think this technique is completely independently stressed. Well, we'll talk about that.
You'll see, we'll not stop talking about it.
So here you changed n to 2 to the n or something. What is this?
Yeah.
I mean, the bipartite, the square root, right? What is it showing for?
Yeah. So yeah. So this is I'm consistent here, but maybe not with the literature. I think I'm consistent here, right? I'm inconsistent here.
In vertices, you get square root n from the Lindsay lemma, and you get square root n over something.
You're right.
Yeah, it's like
Yeah, you are.
It's a number of reads here.
So replace n by log n. No.
It's better to replace the number of vertices by 2 to the n.
Yeah, okay.
Right. Okay. So maybe you should forget about this. This is just to confuse you. And,
You replace the number of vertices, but 2 to the n, and you replace kn by 2 to what's written here.
exactly. So it's like 2 to the little of log n.
That's
Right.
Yeah,
So whenever you see something like that, you should transform back and forth with exponential logarithms. Right.
It's
Yeah.
very hard to compare the tables.
Yeah. But
It's not clear that the last line here is much better than the last line there.
right. Yeah. Fair enough. Right.
So what's
Yeah, but again, the technique is very interesting. Here and that technique was pushed further by Barak, Rao, Shaltiel, and Vigdeson using many new ideas to get something which is this actually.
Better than the what's taking time.
Yeah, so that's what's nice about this result. It's a bipartite construction which improves upon the non-bipartite construction. Okay, so now the problem of constructing bipartite Ramsey graphs seems actually not harder. Okay, and I think now this is the right thing. So we have this should be 2 to the log of log n. This should be, again. But this is the right number. This is what happens when you update your slides, like 2 hours before that. Okay. So looking at these results, our contribution is slightly improving this result towards towards proving or settling Erdős problem, and we give a 2 to the polylog n. This is also correct. 2 to the polylog n Ramsey graph for n vertices. So you want like log n, which is 2 to the log n plus 1 or something, or plus constant. So instead of getting 2 to the log n plus constant, and even instead of getting 2 to the order of log n, we get the second or third function in this hierarchy, which is 2 to the polylog n. This poly is like, it's small. I don't know exactly what it is. It should be larger than 10 or so. It should be small. But reducing the constant here using these techniques it's not clear how you can do that. So you lose some poly again and again. Anyhow, so this is the main result, just quantitatively. And soon afterwards, like maybe slightly more than a month after the publication of this paper, Chattopadhyay and Zuckerman gave a construction of what's called two-source extractor of polylog n entropy. And if you kind of interpret it in terms of Ramsey graph, this gives you also Ramsey graphs with the same bound. In fact, the graph has this extra guarantee that if you take the induced graph on any k vertices, it's not only non-constant in the sense that it's not bipartite, not independent set or clique. It's actually almost balanced. The number of edges is close to half. The density is close to half. And in computer science, this is a very desired property. Okay. So just a roadmap. So this was the problem at hand. For the rest of the talk, we'll talk about the proof strategy in high level. I think it will make it easy to see the proof tomorrow. Tomorrow we'll see essentially the entire proof. So.
If there are 2 to the vertices, you get 2 to the polylog n.
Yeah.
Polylog
Yeah.
n. No.
2 to the polylog n. You can do polylog n means like log n. Yeah. 2 to the polylog n, and you want 2 to the log n.
So I thought you
Because of these lies going back and forth about exponents. Yeah. It is the hardest. Yeah. It's the hardest part of the talk to follow this. Okay, so for the rest of the talk, we'll talk about what's more interesting than the quantitative bounds, just the proof strategy in high level. But in order to do that, we'll have to switch lingo, and instead of talking about graphs, we'll talk about functions, and instead of talking about sets, subsets of this graph, we'll talk about random variables. I would see exactly what do I mean. So this makes a lot of sense when you do, this is kind of the starting point when you try to construct dispersers and extractors, but I think it's a proof strategy. You should think of it as a proof strategy for solving these problems, not as we'll talk about that, in length. And since I don't have the lingo, I can't really tell you what's the rest of the roadmap, so let's continue from there. So what's a disperser? So here will be the definition of a disperser, but before that. In this 85 paper by Shaw and Goldreich, kind of very famous, they define this notion of entropy or mean entropy. So we say that a random variable x, you should think of x as distributed over n-bit strings, supported over n-bit strings, so for some n, ambient n. So a random variable x is called a k-source if you never see a point with probability more than 2 to the minus k. Okay? So k kind of measures the entropy of the source. When k is larger, you have more entropy in the sense that the histogram is closer to be flat, so not with too much high probability points. And just if you don't know this notion, so the largest k for which x is a k source is the mean entropy of k. I will refer to it as entropy. It's not channel entropy, but this is the entropy that we use. And this is, in some sense, the right notion of entropy when you talk about extractors. Not necessarily about Ramsey graphs, but about extractors. So the best way to think about it, if you haven't seen this before, is just to think of, so what's a k-source? You should think of it as a random variable inside 0 and to the n that is actually uniformly distributed over some subset of size 2 to the k. The freedom is just in choosing the subset. And essentially, this is essentially equivalent to the notion of mean entropy. We can show that any mean entropy k source can be written as a convex combination of that, what's called flat sources. But you should think of it this way. This is the best way. But the results that I will state are actually incorrect if you think of it this way. If I define it this way, so I don't want to lie to you, and so I'm defining the right thing. I should ignore it and think of some other thing. So this kind of will replace the notion of a subset. So k will, in some sense, determine the size of the set. 2 to the k will be the size of the respective set. We will see that in a second. So that replaces the definition of a graph. So this is a function. So a function that gets 2 inputs, 2 n-bits input, and output a bit is called a disperser, or actually a two-source disperser. For mean entropy k, if the following guarantee, you have the following guarantee, if you take 2 independent k sources, x and y, and you look at the resulting random variable, d of x and y, this is like deterministic, but this is a random variable, d of xi, then this is a non-constant random variable. This is, with some probability it achieves 0, and some probability you see 1. Okay? And this is kind of the lemma that connects the notion of graphs and subsets of the graph with dispersers or these kind of functions and random variables. So you can kind of easily show, I will say how in a second, that a disperser for mean entropy k with this n, so 2n is the input length, yields a 2 to the k Ramsey graphs on 2 to the n vertices. A bipartite one, even, right. Yeah, this kind of, yeah. For me, this is just a step for proving this one, but yeah, bipartite, yeah. And the reason is you can just, just express these functions in a natural way as a bipartite graph, right? So given this function, you just think of the graph that has 2 to the n vertices of each side. You index each vertex of each side with an n-bit string in an arbitrary way, and an edge is located between a node x and a node y if and only if you see a 1 here. So how this lemma is proven? So actually for bipartite Ramsey graphs, so if you have 2 sets s and t on 2 sides of the graph of size 2 to the k, then you can consider the uniform distribution of each of them. These will be random variables with mean entropy k at least. And the guarantee is that d of xy is non-constant, meaning you see both an edge and a non-edge. All right, so this is a kind of a simple lemma. But I mean, I think that this is a proof strategy, and going to the kind of debate representation of things and working with functions, random variable is a nice step. And there are other examples in the literature I kind of digged in to see who implicitly using these kind of ideas, and there are other examples. I will talk about them later on. So this is the lemma, and this lemma allows us to kind of forget about Ramsey graphs and try to construct dispersers rather than extractors, rather than Ramsey graphs. And okay, so to Noga's question, the main result in dispersers lingo is that an explicit disperser for mean entropy polylogan, and you want to get. So this is what actually thought of getting. But if you want to consider Ramsey graphs, you want to get log n plus constant if you want to actually meet Erdős bound, which should be very hard. I mean, log n plus constant you don't have much freedom there. Okay, so this is dispersers, and with this notion of k sources, so this notion of k sources can be kind of refined in the following way. So I want to define this notion of a block source introduced by Shor and Goldreich. So a block source is a very special k source, okay? An n-bit random variable x, where we split it, say, in the middle to x1, x2, we call this a k block source, not supposed to k source, if in some sense, okay, forget about the sense, if the following holds, if first of all the prefix x1 is a k source, so the first half of it has entropy. But moreover, condition on any fixing of x1, x2 is also a k source, it also has entropy. So x1 and x2 are not necessarily independent, but the entropy of x2 is independent of the choice of x1. Okay, it has entropy independently of the choice of x1. So this kind of sits between one source and 2 sources.
So each of them is half the bit?
This is the best way to think of it. But once you know the partition, then you can define it as you have an index, and yeah. But the best way to think about it is to think of it as just split in the middle. algorithmically, once you know where to split it, then it's all the same. But okay, so this is the notion of a block source. If you think of it, I mean, so a K source kind of is kind of analogous to a set of vertices, because you think of uniform distribution over some set. This is kind of in vertex or sets representation. It's kind of unnatural, right? But if you think of a random variable, it makes sense to consider sources where you can work with the first part, fix it, I mean, work with it and condition on it, and then continue on. So this is one of the reasons why it's nice to move to bit representation. Okay, if this was unclear, then you can erase it. And this is a great theorem by Shin Lee from building on a long line of work from like 4 months before this paper. It's a very new paper. And what Shin Lee is doing here is that he construct these functions, this function, which we call a block extractor, BE. So this function looks like a disperser. I mean, it gets 2 inputs, each of length n, and outputs a bit. It's an efficient computable function, and it almost has the guarantee that we really want. It has the following guarantee: if the first input is sampled from a K block source, when K is polylog n for some fixed poly, and Y is an independent K source, so the first one has to be a block source, and the second one can be arbitrary source. If you are feeding samples to this block extractor from these sources, then what you get is a bit that is not only non-constant, it also has low bias. Okay, it's actually, so it's, in some sense, it already gives you a disperser, a two-source Ramsey graph, a bipartite Ramsey graph, but for each set on the right, but for some weird-looking set on the left, you have this guarantee. Sets that corresponds to K block sources. Okay, and actually, we will use it. Please output more bits than that, and you should also consider the error. So we'll do that next time. But this is a very strong result. It's very close to what you really want. Okay.
So in the definition of a K block source, the partition is known?
Yeah, so once the partition is known, is fine for all of what you want, and therefore you can kind of assume that the partition is in the middle. You can always append zeros, so to make it in the middle. Yeah. But we'll never almost use it in the middle. We'll use it in different places, but assume it's in the middle. It will be the best way to.
So when he says here in the theorem of Lee,
yeah,
or we will assume that
it's in the middle.
For every.
Right. It's just in the middle, because every block, every source is a K block source. There is always an index 2. Right. So you assume. Let's assume it's in the middle, and.
So this is the theorem of Lee is in particular
a free source. Exactly. So he presented it as a free source extractor, and then delve into the details. But it's stronger, and he noticed that. He noticed that it's stronger. Okay.
Can you use it? So just what if you fix? So I want to think about it as a Ramsey graph for square root n versus if I fix the left side of the K source.
So if you think of it as a free source, it's like.
You are losing the entropy in the first part, and you don't get the result. Then it's
Because I thought that for any fixing of x1,
there is
x2
entropy.
is
there
x2
is
is still
entropy.
K source.
Yeah, but the bias depends on the randomness also in the first one.
Well, I guess we just want that it will not be
You are giving up half of the randomness. I mean, why should the result fall?
So again, so we don't know for such a thing what happens if I fix
The x1.
side.
So here you have like x1, x2, and this x3, right? So.
Right. And suppose I fix x1.
Right.
You look at it as a function of x2 and x3 only.
Well, I mean,
Because I thought
the
that for every fixed x1,
x2 has entropy left.
because the trouble is that x1, x2.
If you think of it as sets, then the left hand side set you can partition it in this weird way to, according to the vertex index to. So when you fix it, you just look at subset of the left set. So I don't know what's the implication. So I don't know what's a natural kind of.
I'll tell you, for example, if you fix the left side is x1 or 0, it may be that it has an independence, big independence. So it may happen. And if you fix it to all 1, it may happen that it's.
Yeah, and on average, it's.
On average,
Yeah.
I mean, you need the randomness also in
Yeah.
x1 for this result. For any fixing, you may
Yeah.
not be Ramsey, but on average it is.
Yeah, so you can figure it as a partition of right. it's actually interesting if you have a partition of the left set, such that most of them are fine. So I don't know if most of them are fine. I think maybe each of them is constant. Right, on an average it's fine. It's not like it's actually strong. So yeah, it actually this holds as well. Yeah.
Yeah.
Okay. Okay. So one more thing. So we introduced the notion of a k-source. It's slightly technical talk. So we introduced the notion of a k-source and dispersers, and we introduced this notion of block sources, which are nice k-sources. You have two blocks. And this great theorem that we will use in a black box way, as a key ingredient. And I want to talk further about a notion of subsources. Okay, it's something completely different. So, right, if you look at channel entropy, then it has this nice property that the entropy of the source itself can be written as this way in terms of the entropy of each part, right? This is a very kind of known notion. It's very useful. But in mean entropy, you don't have such notion. Okay, you can show simple examples where this fails. Nevertheless, in BRSW, in this Barak Rausch and Widerson paper, they were able to kind of salvage a corollary from the chain rule that we will use here. They use there. But it's not as clean, so I need to introduce this notion of a subsource. It cannot be that clean, so we need to work a bit harder. So we have the following definition. It's kind of central to this talk. So a source x prime is called a subsource of a source x if x prime is just x conditioned on x being in some event. Okay. And the best way to think about it is, as before, x is a uniform distribution over some k-bit strings, and a is some subset of the support of x, and x prime is then just uniformly distributed over this subset in the support.
I never feel like you can draw pictures of it.
Okay. It's really okay. So maybe, yeah, it's fun. Okay, so you have x. So this is kind of the set on which x is supported on. It sits in like 0, 1 to the n. You can pick the border 0 to the n. It's actually much larger, but it's in like double logarithmic scale or something. 0, 1 to the n. And so if this is kind of the set of x that it's supported on, then you can look at some subset of it and define a random variable x prime, which is uniformly distributed here. And this should be a subsource of x. It's not the most general notion, and the following result won't be true in this notion, but it's still the right way to think about it until the point you need to write the proofs. Okay. And we also care about kind of the density of S of x prime inside S of x. And this is called the deficiency. So the deficiency of x prime, logarithmic scaled, is this expression. So it's, because of forking power of 2, it makes sense to do it this way. Essentially, if A is half the size of the support of x prime, then the deficiency is 1. You lose, deficiency is called 1. And when you so if A is a quarter, deficiency is 2, etc.
What happens to x if you give a few bits of information?
Right, thanks. So yeah, great example. So if I give you, so this is why the notion of mean entropy is the right notion also. So if I give you m bits of information about some random variable x, you can show that there is, say with average, or there is some fixing of that function that, if you condition on that knowledge, you move to a deficiency m subsource of x. Okay, there could be fixings. I mean, if you know a function, say you have a function. Let me just reduce that. Say you know a function. It makes even more messy. Okay, let's say you know a function, 2 bits function of x. Then it could be that it does this thing to x. It's and at least one of them will be of deficiency at least 2 because the size is this quarter. This is the pigeonhole principle, I guess. So, but actually, on average, you also get kind of these things. Okay, so this is the notion of deficiency. And this is the following super cool result in BRSW. It's kind of a lemma, but it's very useful. And it says the following. It says it's not a chain rule. It's a corollary of what would have been a chain rule if it would have existed. So say you have some k source x, and you think you have a b in mind, some parameter b. I think of it as much smaller than k, but still very large to work with, like square root of k or something, k over log n, something that you can continue working on, but doesn't steal the entropy of x. Then what you can show that x might be a bit ugly, and you can't say much about it, but there's always a deficiency 2, which is a quarter of density. A subsource of x, let's denote it x prime, that behaves very nicely. So what very nicely means, so there could be 3 options, and there could be 3 options. And one is that x prime is a B block source. Namely, in some sense, the entropy of x prime is nicely distributed between the 2 parts. So x prime 1 is a B source, and conditioned on any fixing of x prime 1, x prime 2 is a B source. So this is the case where you have, this is kind of a good case for us. Because we have Lee's extractor to work with.
And again, you know that it's half enough?
Yeah, half enough, yeah, just in the middle. Yeah, in the proof actually, yeah.
I guess it's not in the middle.
No, I mean, you can prove it for any, yeah, but it's in the middle. It works. Yeah. The second case that can happen is that maybe the second block is just fixed. The right block is just fixed, or close to that, and essentially the left block steals most of the entropy. Say K minus B. So, and if you think of B as very small, you don't lose anything essentially. And the fourth case is kind of the analog one for the right source, but we need for the right block, but we need a bit more information. And what you can show that you can assume x prime is fixed. So for any fixing of x prime 1, x prime 2 is a K minus B source. So maybe x prime 1 doesn't have much entropy in this case, but for any fixing of x prime 1, so you should think of it as fixed, x prime 2 has most of the entropy. And in some sense, it kind of boils down to this is what you would have expected if, mean entropy is a nice notion of entropy. But you have to move to a deficiency 2 subsource kind of to remove bad examples and stuff like that.
So this is nice because you have like better, now you are talking about n over 2
Right.
bits and you have K minus, let's see, something middle of K.
Right. So
Better entropy rate.
right, exactly. So either you kind of win or you make progress in this respect. But it's you don't know which of these is true, so you need to work. Okay, so let's see. So we talk about dispersers and K sources. I know it's kind of maybe a board talk is more suitable for more than 2 definitions. So recall that a K source is this random variable that is uniformly distributed over a set of size 2 to the K, and a disperser is what we think of as a bipartite Ramsey graph, just this function that has this property that if you feed a independent sample from K sources, you get an unbiased bit. And we talked about block sources and Lee's theorem. So a block source is a nice K source in the sense that the left part has entropy and condition on any fixing of the left part. The right part has entropy. And so Lee says that if one of the sources, you have 2 sources, one of which is a K source, the other is just it's a K block source, the other is just a K source, then you can make sure you know how to efficiently output a non-constant, even slightly unbiased bit, or even very unbiased bit actually. And we talked about the chain rule for mean entropy, namely that we just did it. So any source, K source, has a low deficiency subsource that behaves nicely. Either it's a block source with parameter B, think of B as small but not too small, or in the other cases, one of the half steals the entropy, essentially all of the entropy. And now I want to talk about the high-level strategy of the proof, and it will get refined and refined until we will be tomorrow. We'll talk about tomorrow. So here's the high-level proof. It completely flowed, but it's still a starting point. So given x and y, sample from x and sample from y, these are 2 K sources, not block sources, right? Given x and y, sample from x and y, we'll compute some subset of the indices, just indices. Let's call it B, such that x sub B, namely the marginal distribution of x restricted to that block, is a block source. So when I don't say what K is, I just mean large enough K block source. Okay, just polylogans block source. Yeah.
Related to the B in the previous slide.
There was a B? There was a B. It's completely different. Right, I didn't notice. Initially, it was a capital B, and now I see that. Okay, right. Thank you. It's a very different B. This is a B for. Oh, they stand for the same word, block, but in a different meaning. So, anyhow, yeah, it's a different B. So once you have this. I mean, naively, or even naively, it fails. But anyhow, you can just apply Lee's extractor to xb, which is a block source, and y, which is a K source. Of course, it makes no sense because the source that you apply here is a function also of y, because b is a function of y. Right? So the first source and the second source are dependent. So even though this is a block source and this is a K source, they have to be independent to apply Lee. So you cannot do that. No, it does. Any independent, yeah. You can never.
require independence inside the X1, the partition
Right.
between the
Right. Yeah. Great. You have to have a dependence, independence. So this is wrong, but you can write it this way. Now it makes sense. So what we'll do is we'll compute B, some block, such that B is fixed, namely reveals no information, on some subsources, x prime of x and y prime of y. There will be a picture soon. On top of the previous property that x prime B is a block source. So now we move from x and y to x prime and y prime, which is our subsources. And the guarantee is that on these x prime and y prime B is fixed. And moreover, x prime B is a block source with high enough entropy, so you can really do output this thing. So why does this work? So just in a pictorial way. So this is x and y. It's kind of the Poynter distribution of x and y. I mean, it is picture clear. I guess it's what you think of it. And so what you can show, the high-level strategy will be to find, for the analysis, subsource of x, which we call x prime, and subsource of y, which we call y prime. Notice that if you are a subsource, if you are two subsources of two independent sources, respectively, then you are also independent because just subsets. So this is again, it's like this rectangle thingy. And what you will be able to show that, okay, so B, on each of these points, B will be a different value. This interval will be different. But on all of this rectangle, it will be the same value again and again, 1 to 5, okay? So knowing B doesn't introduce correlations between x prime and y prime. And so Lee's construction actually does give you an unbiased bit here. And this is enough for us, because we just want to be a non-constant on the entire thing. So being non-constant on some nice subset is fine. Right, so there is something to it. I mean, when you work, it took me time to figure this out. When you work with algorithms that get samples from distributions, the algorithms get strings, but the analysis works with distributions, right? So there are two different inputs, kind of the one that you think of it, which is the random variable, and the one that the algorithm is allowed to look, which is the strings. So when you want to construct dispersers, and this was already noticed by BKSSW, it's kind of a simple observation, but it makes a lot of it's a very strong observation. You can kind of make the thought experiment where you replace, you're not happy with the original sources that you got, and you can just replace them with subsources.
So that's why you are very far from getting.
Yeah, exactly. Yeah.
Can you explain again why x, b, and y are independent now?
You have to make them.
But yeah, we still use y prime. So
Right.
y prime and y are.
Yeah, but the only information moves from y to this x prime b is just b.
What is x prime b actually?
Yeah.
It's
So it's a subsource of x prime.
no, okay, x prime b. Sorry, x prime is just an n-bit string, n-bit random variable, and b, maybe I can write it down for a second, because so what you actually compute is this thing. So this is a little x. This is what you compute, and you know that restricted to this subsources x prime and y prime that we need to find, you have this random variable is just this thing. So, because b is constant on x prime and y prime all along. It should be a subset. I don't know. So in particular, it's independent of y prime. The only information that creates the correlations is the b. So if it's fixed, it never gives you any correlation. It never gives information. There are no correlations.
On every member of x prime and y prime, b is the same.
Right.
That's how you choose them.
I mean, the only problem you had is that this random variable is correlated with y prime.
Okay, so b is not a function of x and y, it's a function of x prime.
Okay, so it's a function of the string x and y. If you sample little x and little y, this little x and little y from big x and big y, you're destroyed. You can't say anything. But if you sample them from x prime and y prime, which are suitable subsources, such that you know that this b is, to begin with, just some constant, then
So what I'm saying, so is it true that b is a function of x prime and y, capital X prime and capital Y prime?
So
It's a function of individual strings. It's a function of the Boolean cube times the Boolean cube.
yeah. No.
It happens to be constant
Mhm.
on this little square.
Yeah, it's
You have to find the square on which it is
Right.
constant, and you have to make it big.
Okay, so the claim is that there exists such a
yeah, exactly.
rectangle on which
B is constant.
there exists a B and a rectangle.
Exactly, and they are depend on each other, but you don't not like
Okay,
probabilistic
so when
dependence.
you have
Just
a sample from Y prime, it doesn't say anything
Exactly.
about the other parts of Y.
yeah. So the Y prime is a random variable, but this doesn't. This is just fixed, so it doesn't look. I mean, you can just replace it with this fixed thing.
This will always be 5 and
Yeah, exactly. So
Just define x prime and y prime with xy condition on this value being b or something like this.
So instead of talking about conditions, because I'm kind of, we just move to subsources. You can think of it as x prime is x condition on this event that makes it, but it's the same thing. But yeah,
You're doing two steps of conditioning, right?
Right.
First, you move from x to
Right.
x prime, and then from x prime.
right. So we don't do a conditioning in the sense that yeah,
But
it's
x prime b is the same. It's not really shrinking, but it's the same value.
exactly.
Okay.
So it doesn't make any further conditioning.
Okay.
Right. Yeah, it is. I mean, I won't deny it. It's kind of confusing because, the algorithm works on strings, and but for the analysis, you are always allowed to move to subsources, which is amazing power. You can change the input in some sense, right? Not the strings, but the input from which you came from. Yeah.
Does the function b trace the net answer, or is it computed?
No, it's computed. It depends on x and y. It's
It depends on the inputs.
yeah. And in different points here, it will give you different b's, but all of here it will give you the same b. So it is depend on little x. It applied to 0, 1 to the n on 0, 1 to the n, so give you different things. But you are guaranteed. So I mean, the high level strategy kind of goes by saying that for any x and y, which are kind of little in 0, 1 to the n, there is a subsource of x, which is x prime. X prime's identity depends on x and y, but not on the samples, little x and little y. Hopefully this doesn't make more further confusion. And also y prime depends on the sources, the kind of the underlying distributions of x and y, but not on the samples. And so this is why we work with distributions. Kind of you need to think of two different sets of inputs: the strings and the random variables for the analysis. And you can do this trick. Where you
Think of it as a Ramsey theoretic result. In every
Yes.
graph, there is a subgraph which has this
Yes.
fantastic property that it defines for you this B. And this B actually partitions X prime to two part, makes it a block. So it's
right. It's a of non-independent
so the
distant Ramsey
subgraph
results.
depends on the graph.
Right. Of course. Yeah. Right.
It can be computed only for the sample, from two samples. That's it.
Yeah. B can
So
compute
not
for
only
those
a
samples.
function of x prime. So the small x and y let you approximate. I don't know. Let you give you some information of x and big y, and then. Okay.
I'll agree. Okay. I mean, I think I understand what you said, and I'm fine with it. Yes. Okay. So, yeah. So this is a 50-minute talk.
Yeah, roughly.
55 minutes.
Yeah.
Okay. 60. Okay. That's
Depends on the number and quality of the questions.
okay. So 45 minutes talk. 45 minutes talk. Okay. Okay. So for the answers, not the questions. Okay. So it just means we have to spend 3 hours tomorrow. That's the only current. So okay. So there is one question that is there such a B? I mean, is it true that in any source X, forget about finding it. Just you're given an random variable X, and then bit random variable X. Is it true that there is some subset of the indices such that restricted to that indices, you get a block source? And I don't think it's clear at all. So before even trying to compute it, let's verify it exists. And while at it, we kind of understand more the nature of this B. Okay. So you can forget about the second source. You have one source now, X.
You said something about the efficiency of
Two,
x prime.
Yeah,
In the previous.
No. So this is not. So okay. So 2 was to get a. Okay. So 2 was if you have a K source, you can move to a subsource that is either a block source but the deficiency here of X prime and Y prime is polylog n or something. because you will, yeah.
Well, it's important to examine.
Right. It's polylogarithmic. And this is, okay, we'll talk about it later. It's not much, but it's not too little.
So you really want B to be like efficiently computed?
Yes. And it will be. And it will be on low efficiency, which makes some I care to some extent. So why do you have this B? So this kind of leads to the notion of entropy trees, which was implicit in BRSW, and we make it slightly more explicit because it's now we have the tools to clean it up a bit. So, and the tools okay. So recall this chain rule for mean entropy, right? So you have a k source x. You know that for any b that you want, it should be kind of non-trivial, but for any b that you want, either the thing is either your source has a deficiency to subsource, which is a b block source, or otherwise, in some sense, one of the sides steals the entropy. And here is a kind of an easy corollary or claim, I'm not sure, is that, so we want, given k source x, we want to find this b, just for the analysis, to show the existence of this b. So here is an easy case, right? I mean, it's not easy. You need this lemma, and this lemma is not that trivial, but it's easy given the lemma. So any 0.6 or something, any larger than 0.5n, any 0.6 source has a deficiency to subsource that is a 1.n block source. Okay, so if you have a source with efficiency 0.6n, it does make intuitive sense that no half can steal all the entropy because the length is just half n. And this makes it more precise. It says that if you have entropy larger than 0.5, say 0.6, then if you just clean it a bit, you move to low efficiency subsource, then it's true that it's really a 0.1 block source, 0.1 n block source. Namely, the first part has high entropy, and conditionally the second part has entropy. No one can have all the entropy. And to prove this, is just apply this lemma. So with k, which is 0.6n, and b, which is slightly less, 0.1n minus 1 or something, but forget me about it. So notice that the first case is what we want to prove, that there is a deficiency to subsource of x that is a 0.1 n block source. So if we can only rule out the other two cases, it would be great. And you can, just because the other two cases says that, for example, the first one says that x prime 1 is a 0.6n minus 0.5n plus 1 a source, which is impossible because its length is smaller than 0.5n. It is 0.5n, so it's smaller than the entropy that you claim. Right, a source of length n has the entropy.
So 0.6 is just
half plus delta.
plus 0.1.
Yeah.
Right. Yeah. Right. But it took me a while to choose this number so that the second thing will be easier to grasp. So 0.6 is the best number you can have pedagogically to show the next claim. So, but anyhow, here in this case, b is just everything. B is just 1, 2 till n, right? This is the b that you care. In the sense that, if you have a source of mean entropy 0.6n, then it has a deficiency to subsource that is by itself. We don't have to move to some indices. By itself is a 0.1 n block. So what happens? So this is a nice corollary that, but let me skip it for a second, okay? What happens is if the entropy is slightly smaller, say 0.4 n. I mean, this is problematic now because it could be the case that one of the sides actually have all the entropy inside. One thing to do is just to move to smaller blocks and make sure that none of them can do it. But this is kind of the BKSSW way to go. It will only lead you to something like supporting entropy to square root of n, so we won't go there. What we will do is we'll show the following thing. So these things are kind of from BRSW. I still haven't got to. So these things you can find implicitly in BRSW. So any 0.4 n source x has a deficiency 4, not 2, but 4. Let's call it x prime, such that one of the following holds. Either x prime itself is a block source, which is great, so b is just everything. Or otherwise, essentially, one of the halves is the b. We don't know which, but one of them. Namely, the other scenario would be that x prime 1 is a 0.1 times its length block source. Or it's fixed, and x prime 2 has this property. You can, for any fixing of it, x prime 2 has property. So how you can prove that? So you just apply this, again, this chain rule, for mean entropy with 0.4 n as k and 0.1 n as b. No, it's really 0.1 n, I think. Even. So either you will get that x prime itself is a 0.1 n block source, which is great. Or otherwise, say consider just the second case, the first case is the same, you get that x prime 1 is a 0.4 minus 1, which is 0.3, and source. So the entropy was reduced to 0.3n, but actually the entropy rate is now 0.6 because the size is n over 2. Yeah, exactly. So and now you are in the scenario that you handled before, 0.6. So you can find another deficiency to subsource of this part, which kind of induces a subsource to the entire thing, which is a deficiency before, and you have this property on here. Okay, so more generally, if you have an x k source, if you have a k source x, and set b to be say k over log n, just it will be useful for us. This is the right setting. Then let's just apply it again and again. So we handled k, which is 0.6. This was kind of trivial. We handled k, which is 0.4. This was like 2 trivial steps. And now we'll make log n trivial steps. So you have this random variable x. It's a k source, and k is much smaller than 0.4, and it's polylog n or something. It could be anything, you would say. So.
But already with the 0.4 and you're facing a problem
Right.
with that because you don't know in which case.
Right. Yeah, I'm kind of forgetting about finding it, just proving its existence now. Right, that's true. And in tomorrow I will talk about the harder problem of finding this b, and we won't actually find it in a clean way. We'll have to walk. But anyhow, we'll see. Exactly. Exactly. Yeah. It's an efficient computer, so it should be fast. But,
It is a good philosophical point to consider. I mean, you want to find where the entropy is.
right.
But you are not given the source. You are given only a sample. A sample has zero entropy.
Yeah, it makes
That's a challenge.
it's
So you should
yeah.
think about it.
it's magical, and this magical is being resolved by the channel response mechanism. But this is kind of okay. So just maybe we'll end after this slide essentially. So say you have an n-bit source x. What we will do is we apply this chain rule again and again, figure out where the entropy is, and log our steps in this tree manner. So say you have this x, which is an n-bit random variable, and this is the starting of a tree, a kind of binary rooted tree. So say you apply this lemma, and you got that there is deficiency to subsource of the source, such that the first part is fixed and the second part has most of the entropy, k minus k over log n. So you draw it this way. So here you kind of, this is fixed, and you move here and you apply the lemma here again. If you apply the lemma here again, you might find out that the second case happens, and you find the deficiency to subsource of the subsource, the previous subsource, such that this thing is a k minus little of k source. So you move there. And then you apply it again, and because I had some room, I added more. So maybe now this part is fixed, and you move to talk about the kind of, I think, 6th or 8th of the source. And then you discover that it has a deficiency to subsource, which is a block source. So this will be, in this case, this will be your b, your block. I mean, the little b that is, I'm not sure exactly where it sits, but you get a subset of the indices where you have this block source. And what I claim is that for any k, which is I think should be larger than like log square of n or so, you are bound to found at some point this block source. And the reason is exactly what you said. So essentially, in every step that you haven't succeeded yet, the length is decreased exponentially. I mean, after our step, it decreases exponentially, but the entropy decreases just linearly. So at some point, you will have, as long as you haven't succeeded finding the block source, you will have a source on n times 2 to the minus r bits. And the entropy will be almost k minus k over log n times r that you did. So in more exactly, you'll have a deficiency to r subsource that has this property, but forget about that. And at some point, the entropy will catch up with the length, because so once this is larger than 0.6 times this, in the next iteration, you'll find the block source.
So when you're fixing, you arbitrarily fix it?
Yeah. Yeah, arbitrarily. Yeah, it's actually a stronger notion. It's actually you get a convex. Yeah, but you can.
So if you get one to the top, okay, the first one is just what you want, the first property. The second.
Right. And the second and third, I mean, okay.
The second is you just get rid of the.
The right part. Just concentrate on the.
Okay, so this
Right.
is just you got 3, and then.
Yeah, now I see actually that the fixed thing is not necessarily to show that B exists, but it will be important for finding it algorithmically. So I could have just removed that and say the same thing.
And then you claim that eventually you will get.
Right. After log n over k iterations, you just need this to be larger.
You cannot condense forever.
Right, exactly.
You increase the entropy rate, and you cannot increase above 1.
Okay, so yeah, so after log n over k iterations or so, as long as k is large enough, like log square of n, just do the math. You will find some subset of the indices. It's also a structure, not just subset of the indices, associated with this tree that this is a k over log n, this is b, k over log n block source. And if k is like log cubed of n, you still have much entropy to work with. And as a claim that we will take from today, and we'll skip the rest, any k source x has a deficiency at most 2 log n subsource x prime that has this nice tree structure. So we call this kind of a source x prime that has this structure. We call it a tree structured source because its entropy is described using this nice tree. And not any source, just by counting, you can show that not any source has a nice structure like that, but any source has a low deficiency subsource that has structure.
Why do we care about the tree structure?
So algorithmically, we will, I mean, if b, little b, would have been some subset of the indices, I'm not sure how to find it. But here, you just kind of need to find the node that is associated with it. So we will, algorithmically, we'll work with these trees, and we will find this b.
And why is this the right efficiency?
Because, okay, so it's actually, so every,
Entropy is smaller than k. That's all the entropy you lose. So you want to have still, essentially as much entropy as you start.
so this is why you can lose this log n, and the reason you lose it because you do.
Works even for bed sources where k is log n?
Yeah, log n is you need at least log square of n, because it just
Okay,
so polylog n, yeah.
So for very bad sources, it's still
Yeah, it still works. You just need to dig low enough to find it. So
So if you get something more than log n, then it wouldn't be applicable.
yeah. I mean, the real loss is here actually, the k over log n rather the minus 2 log n in some sense. So anyhow, so I think I'll wrap up because it's like 56 minutes, 7 towards ranging to 7. So I did have a lot of slides going through, and I thought I'll have some more time.
But yeah, you can,
Do it tomorrow. Start tomorrow.
56 minutes, you can, don't go, well, anyway, end in a graceful way.
Yeah, of course. I'm just trying to, yeah. yeah, just.
Yeah, that's very graceful.
Yeah, I just meant to. I didn't. Yeah. So, but I do want, if you are not planning on coming to the next lecture, I do want you to have the open questions, if that's okay, just 1 more minute or so. So quantitatively, our results give 2 to the polylogarithmic Ramsey graph, and Erdős challenge is 2 to the, I mean, if you look at it in this exponential thing, 2 to the log n plus constant, and the next natural goal will be 2 to the order of log n. There are at least like 4 or 5 points in the proof where you lose this in this poly, so you saw already one of them. So this will be tricky. Now, even a weaker notion of explicitness is interesting. I'll talk about that tomorrow, actually. What I do want to talk about is, to mention is that we don't have a simple construction like Franklin and Wilson has that is very succinct and kind of clean. Even for very weak parameters, we don't have them. So this is very interesting still.
Even if it's less efficient.
Right. Yeah. So you can combine these two exactly. Yeah.
Certainly, I mean, we cannot ask Erdős now, but certainly he would prefer something
Right.
that says he looks at the bits of pi.
I agree. Yeah. I agree.
It's a bit of a,
Hey, he's only giving $100. There's a limit.
Right. It's a year of effort here. So. And one other thing, just because I think it's really interesting. So what happened here? I mean, we kind of used to it because we're doing computer science. But what happened from the original point of view? We moved to the Brit representation of the problem. Namely, we think of these vertices. We look at the bits representation of them and argue about the bits, right? Because we moved to disperser lingo. And it's kind of weird if you look at the original problem. I mean, the name of the vertex shouldn't matter that much. I don't know. It shouldn't have come into the analysis naturally.
also in Frankel-Wilson it does.
Also in Frankel, that's
modulo
true.
prime.
That's
not-
true. So
you
it's
have
the
to
same.
know that, I mean, what you-
No, but the Brit looking at the Brit representation.
Some representation, you have to use the representation. And you are constructing a graph. What does
Okay.
cosine function.
Okay, that's fair. That's fair. Yeah.
You
You need to look at the
You have
vertices.
to look at it.
Yeah, and for looking you need naming. Okay, but anyhow, the bit representation, which is for small primes, okay, is also used by in this randomness efficient isolation lemma proof, which you can look at. It's kind of surprising to see it there as well. Okay, well, thank you. Continue tomorrow.